All right, let's go through paper 6, which is the alternative to the practical for chemistry. This is IGCSE from Cambridge International Examination, CIE, from October-November 2018, variant 2, so the code is 0620/62. All right, let's get started.
Go! Well, let's rock.
Question 1. Magnesium ribbon was burned in air. A. Complete the box to name the apparatus. Okay, so that thing that holds the magnesium so your fingers don't have to, they're called tongs. All right. B. Suggest the appearance of the product formed when the magnesium ribbon was burned in air. So the product formed is a white powder. You can call it a white ash, white solid. You could also say smoke, but the white powder is what they're looking for. C. Name the product formed when the magnesium ribbon was burned in air, and the product formed is magnesium oxide. It's reacted with the oxygen. The magnesium is reacted with the oxygen to produce magnesium oxide. The product from burning the magnesium ribbon in air was added to water and heated. The solution formed was tested with universal indicator solution. D. Suggest why the product was heated after it had been added to water. Explain your answer. All right, so it was heated so that more of the solid could dissolve, and it takes less time for it to dissolve because things dissolve faster when they're in warmer water. So to dissolve more solid at a faster rate. 1 mark for saying you want more of the solid dissolved, and the second one saying the rate of the dissolving will be faster. You could also say to make it dissolve completely. E. Suggest the pH value shown when universal indicator was added to the mixture. Well, you should know that when magnesium oxide is added to water, and heated, then it becomes alkaline. Okay, and you don't have to know exactly how alkaline. It has to basically be anywhere between 7 and 14. If you had any answer greater than 7 and less than 14, that would be okay. I'm going to say pH 9. You don't have to know exactly what it would be. And F, state one safety precaution that should be taken when magnesium is burned in air. Now, the biggest safety concern with magnesium being burnt is the fact that the burning is so bright. It's not like most of the things you burn. It is so bright it can easily damage your eyes. So first of all, one thing you could say is goggles. Wear goggles. Wear safety goggles. Okay, goggles will protect your eyes because you don't want sparks of magnesium flying into your eyes. That would be very, very painful. And the other thing is that because it's so bright, if you hold a blue glass in front of the flame, then you can watch the flame and not damage your eyesight. Okay, just choose one of them. Those are the 2 answers they're looking for. Question 2, the experiment question. A student investigated the rate of reaction between solution L, solution M, and hydrochloric acid. When these chemicals react, they form iodine. So sodium thiosulfate solution and starch solution were used to show how fast the reaction proceeded. Okay, when you have sodium thiosulfate and starch reacting with iodine, you get a blue-black solution. It becomes blue-black, and the blue-black is the endpoint they're looking for. So experiment 1. A measuring cylinder was used to add 10 centimeters cubed of solution L to a conical flask. Okay, so what do we have here? We have a conical flask. All right, and we add 10 centimeters cubed of L. Okay, we then add 10 centimeters cubed of dilute hydrochloric acid. Okay, so 10 centimeters cubed of HCl. All right, 10 centimeters cubed of sodium thiosulfate, 10 centimeters cubed of sodium thiosulfate, and 1 centimeter cubed of starch. Lots of things are going into this flask. 1 centimeter cubed of starch. And then, once all these things are added, the reaction was started by using a measuring cylinder to add 10 centimeters cubed of solution M. 10 centimeters cubed of M. All right. Then once all those have been added, the reaction will have started, and then a timer was started immediately, and they swirled the mixture. The time taken for the mixture to turn blue-black was measured, and the conical flask was emptied and rinsed with distilled water so they can do it again. So experiment 2, a measuring cylinder was used to add 8 centimeters cubed of solution L and 2 centimeters cubed of water to the conical flask, 10 centimeters cubed of dilute hydrochloric acid, 10 centimeters cubed of sodium thiosulfate solution, 1 centimeter cubed of starch solution were then added to the conical flask. The reaction was started by using a measuring cylinder to add 10 centimeters cubed of solution M to the conical flask, and the timer was started immediately, and the mixture was swirled. The time taken for the mixture to turn blue-black was measured, and the conical flask was emptied and rinsed with water. Okay, it sounds like a lot, but everything is exactly the same except the first step. Okay, so now we have, instead of 10 centimeters cubed of solution L, we had 8 centimeters cubed of L and 2 centimeters cubed of water. All right, so basically it's becoming more dilute. The third experiment, they only changed the first bit. They didn't rewrite out the entire thing again. Experiment 2 is repeated, but we used 6 centimeters cubed of L plus 4 centimeters cubed of H2O. So each time it adds up to 10. So experiment 1, there was 10 centimeters cubed of L, then 8 centimeters cubed of L, then 6 centimeters cubed of L. Experiment 4 will be 5 centimeters cubed of L plus 5 centimeters cubed of H2O. And then experiment 5, we have 3 centimeters cubed of L plus 7 centimeters cubed of H2O. So it looks like a complicated experiment, but once you read past the first bit, it gets very straightforward. All they're doing is changing the concentration of L. A. Use the stop clock diagrams to record the time taken for each experiment in the table. Okay, so we have the experiment numbers down the side. It obviously doesn't all fit on the screen. Then we have volume of solution L, volume of distilled water. Then we have the stop clock diagrams. All right, so the inner circle shows about minutes. Okay, here, these two, they're at 0 minutes, so everything's in seconds. You always write your answer in seconds, especially if the top up here it says in seconds. Be very clear with that. All right, so we look at this, and if we only look on the outside, we see it's at 29 seconds. Now, if I write it like that, I'd lose a mark. You don't put the units in the table. That's wrong. There we go. That's better. All right. So again, the minute hand is at 0, and the second hand goes all the way to 30, 35, 36, 37, 38, 39 seconds. Good. And now we're looking at experiment 3, 4, and 5. So at experiment 3, again, the minute hand's at 0, and the second hand goes all the way up to 45, 50, 55, 56 seconds. Okay. Now if we look at experiment 4, the minute hand's at 1, so that's been 60 seconds past. 60 seconds plus 6 seconds, so that is 65 seconds. And so if we look at experiment 5, you can see the minute hand's at 1 minute, so that's 60 seconds plus 15, 30, 45, 50, 51 seconds. So 60 plus 51, that is 111 seconds. All right, there we go. Now we can move on to the next bit. B, plot the results for experiments 1 to 5 on the grid and draw a smooth line graph. A smooth line graph means do not use a ruler. All right, a smooth line graph. It can either say a curve, and that would be not use a ruler. A straight line graph would be using a ruler. So you have to be watch very carefully up here. If it doesn't say what it is up here, then you just look at the graph and see what is logical. Are the points in a curve? Well, then obviously you draw a smooth. Are the points completely straight? Then you use a ruler to go straight up, although you don't go beyond the points you're given. You just go to the points you're given. All right. Okay, well, it almost fits on the screen, but not quite. I'm just going to fill in the points, and then we'll draw the curve. Okay, so these are the points. We have 10 centimeters cubed for L. We have 29 seconds at 8 centimeters cubed. We have 39 seconds at 6 centimeters cubed. We have 56 seconds at 5 centimeters cubed. We have 65 seconds, and at 3 centimeters cubed we have 111, which just shows up on the screen. Okay, remember, if you want to know how much each little square is worth, we're going up by 20 seconds per big set through 10 squares. That means 20 divided by 10, 2 seconds per square. And if you notice, I did the dots, I did the points as little X's. They want to see little X's, they don't want to see little dots. A little dot like this, and you draw a line, and not a line like that. You draw a dot like this, you draw a line, and it can be very difficult to see where the point is. Okay, so you need to make it clear where the point is. You also can't do a big blob, because then it's hard to tell the exact point. Okay, it's quite hard to draw a straight line on this computer, but this is reasonably good. If you notice, it is curved, and that's what it said to do in the question. And I would recommend erasing some of this and trying to draw it neater, but as I said, it's quite tricky to do with this system. And make sure you draw it in pencil so you can erase it, because unless you're very good at having a very steady hand, it's difficult to get right the first time. All right, let's move on to the first question on the graph. Question C. From your graph, deduce the time taken for the mixture to turn blue-black if experiment 2 were repeated using 4 centimeters cubed of solution L and 6 centimeters cubed of distilled water, and show clearly on the grid how you worked out your answer. All right, so we're looking for the time at 4 centimeters cubed. Okay, so if we take the time when L is at 4 centimeters cubed and draw a line all the way up. All right, and if you notice, that is where it ends. And now we take that point where it crosses and put it over to the axis. All right, that's showing clearly on your graph how you got the point. Okay, so this point here is 80, 82, 84, it's about 86 seconds. All right, your graph may be slightly better because you may have drawn your line a little bit neater, or maybe less neat, I don't know. But it depends on how you drew your line as to the exact spot. But as long as you've shown clearly on your graph that you can measure the point at 4 seconds, all should be good. So 86 seconds. So it took 86 seconds. If you don't put the unit in, you lose a mark. 3 marks. 1 mark is for showing clearly on your graph, 1 mark is for reading it correctly, and 1 mark is for the time, putting in the units. D1. In which experiment 1, 2, 3, 4, or 5 was the rate of reaction greatest? All right. So remember, at 10 centimeters cubed for solution L, this was experiment 1. This was 2, 3, 4, and 5. Don't write these numbers on your graph. This is just me showing you. So experiment 1, the reaction happened the fastest, which means the rate of reaction was the fastest. So in experiment 1. Good. 2. Explain in terms of particles why the rate of reaction was greatest in this experiment. Okay, so particles, basically in the first experiment there were more particles of solution per volume, and so that means that the collision rate was faster. There were more particles of solution L per unit volume, so there was a higher collision rate. So they're talking about more particles, because they say in terms of particles, and they want to know the collision rate. Because anytime they talk about particles, they want to know about the rate of collisions or effective collisions. E1. Suggest an advantage of using a graduated pipette instead of a measuring cylinder to measure solution L. Well, graduated pipettes, because the diameter of the tube is narrower than the measuring cylinder, they're more accurate for measuring the solution. It measures the solution more accurately. And 2, suggest and explain a disadvantage of using a graduated pipette instead of a measuring cylinder to measure solution M. So the reason why in this particular experiment a graduated pipette might not be the best solution is because it is much slower. And as you're trying to time in seconds very accurately from as soon as the solutions touch, then it's not going to be as accurate. So one way it increases the accuracy, one way it decreases the accuracy. So it is slower to add the solution, so the measuring time is less accurate. And F suggests one way to improve the reliability of the results of this experiment. Whenever it says reliability, it always wants the same answer. Repeat and take the average. So repeat and take the average. That's always the answer when they say reliability. How can you rely on your results? Because you've done it more than once. Question 3. Solid N and solid O were analyzed. Solid N was ammonium sulfate. Tests were done on each solid. So the tests on solid N, ammonium sulfate, what they did first is they just looked at it. Complete the expected observations. A. Describe the appearance of solid N. Solid N is a white crystal because it is a salt. White crystals because it's a salt. Solid N was dissolved in distilled water to form solution N. Solution N was divided into 2 portions in 2 test tubes. So the first one, dilute nitric acid and aqueous barium nitrate, were added to the first portion of solution N. And so what did you see? So if we have nitric acid and barium nitrate, what is that? That's a test for the sulfate ion. It's SO4 2-. Now as the salt is ammonium sulfate, we're going to see a positive result. So what do we see? We see a white precipitate. A white precipitate. C. Aqueous sodium hydroxide was added to the second portion of solution N. The mixture was heated and the gas produced was tested. Okay, so what did you see with aqueous sodium hydroxide being heated and then the gas tested? Remember, it was ammonium sulfate. What you're going to have is ammonia gas, and so ammonia gas turns red litmus paper blue. So the gas turns red litmus paper blue because it's a very alkaline gas. D, name the gas produced in C. Well, that is ammonia. Now be very careful. Remember, ammonia is the gas. Ammonium is the ion. Okay, so it's not ammonium, it's ammonia. So now we do the tests on solid O. Some of the tests and observations are shown, and the appearance of solid O was studied. Okay, so when we added distilled water to some of the solid O to form a solution O was divided into 2 equal portions in 2 test tubes. And there were 3 tests performed on that solution O. All right, so test 1. An excess of sodium hydroxide was added to the first portion of solution O, and there was no reaction. All right, so that shows quite a few things that it's not. All right, and it shows a little bit of what it is, but we'll move on to the next one. Test 2. Dilute nitric acid and aqueous silver nitrate were added to the second portion of solution O. Now, nitric acid and silver nitrate, that is a test for the chloride ion. Okay, so the white precipitate means it's a positive test. So that means there is the chloride ion present. Test 3, a flame test was done on the rest of solid O. Well, the lilac colored flame test that shows it's potassium. All right. E. What conclusion can you draw about the identity of solid O from test 1? Now this one's kind of tricky. Normally you just learn what the tests are. Now you have to try and remember what the tests aren't. All right, so the ions that you know of, that you should know, pretty much include things like calcium, copper, iron, zinc. These are ions that all have a positive test when you react them with sodium hydroxide. Obviously anything to this on this side of the periodic table, that is not going to count because we're only looking at cations. And so those are the only ones that we're looking at for the reaction with sodium hydroxide. So we have transition metals, we have group 2, but there's nothing here in group 1. So what this indicates is that the cation, and remember cation being C-A-T-I-O-N, cation is the positive ion. Okay, the cation is in group 1. That's what it indicates. So the cation is from group 1. F, identify solid O. Well, solid O has potassium and the chloride ion, so it's potassium chloride. All right. Question 4. When solid C and solid D separately react with dilute hydrochloric acid, one reaction is exothermic and one reaction is endothermic. Plan an investigation to determine which reaction is exothermic and which reaction is endothermic. And you need to say which energy change is greater. You are provided with solid C and solid D, dilute hydrochloric acid, and common laboratory apparatus. All right, so whenever you're answering these questions, you should always think the basic things that you need to include in it. You need to include the dependent variable, the independent variable, the controlled variables, or some controlled variables, and something about the method. Okay? Often you want to put in something about reliability. There's no remark for reliability in this one. Remember, reliability is when you repeat and take the average. Okay? Other things you need to include in this investigation, you need to include which reaction is exothermic, which is endothermic, so that's your observations. And how do you know which energy change is greater? You have to put each one of those in. It's a 6-mark question. You'll have 1 mark for making sure you answer the first one, 1 mark for making sure you answer the second one, and then you need to show your investigation. All right, so you need quite a few bits. Before you start writing out these questions, find a blank page, plan out what you're going to write, make sure it's in the right order and you haven't missed anything, and then put a big line through it to show the examiner not to mark that. That way, it'll make it nice and easy for the examiner to read. If the examiner finds it difficult to read, they'll also find it difficult to find you the marks. Okay, so what do we do? This is one of those reactions where you take a polystyrene cup and you add the solution and you put in some solid and you measure the temperature with the thermometer. The temperature change with the thermometer while stirring it. That's pretty much all that you're doing with this one. Okay. So first of all, you need to measure out, let's say 20 centimeters cubed of hydrochloric acid using a measuring cylinder into a polystyrene cup. Why 20 centimeters cubed? Because you have to choose a number. You could have said 100 centimeters cubed. You could have said 25 centimeters cubed, 50 centimeters cubed. It doesn't matter. Just choose a number. So measure out 20 centimeters cubed of hydrochloric acid using a measuring cylinder into a polystyrene cup. It doesn't have to be a polystyrene cup. It can be something else, a test tube. It can be a plastic cup. It could be something, but you have to actually choose a suitable container to put it in. Okay, so next step is you need to record the initial temperature of the acid. So record the initial temperature of the acid. Then you add some of the solid C to the cup and you stir it. I'm going to say 15 grams. Why? Again, you just need to choose a number. Add 15 grams of solid C to the cup and stir. Is that too much? It might be, but you just have to choose a number. All right, once you've added that, you've stirred it, it's all dissolved, then you record the final temperature and calculate the temperature change. So you record the final temperature and calculate the temperature change. That's the important bit. And then you take all of that and you do the same thing with solid D. So you repeat the procedure with 15 grams of solid D. You're comparing the two. Okay, so what have we done? So with the dependent variable, the independent variable, the thing you're changing whether it's solid D or solid C. So you have the independent variable. You're measuring the temperature change. Okay, so we have the final temperature change that's included in there. Controlled variables using the same amount of hydrochloric acid, and in the same cups or same type of cup. So you have a couple controlled variables, and you're talking about the method. Okay, now what you need to include are the conclusions, 2 of the 6 marks. So how do you know which reaction is exothermic and which reaction is endothermic? Well, if it's exothermic, it's going to raise the temperature of the thermometer. The thermometer is going to read a higher temperature. So the temperature increasing shows an exothermic reaction, and the temperature decreasing shows an endothermic reaction. Don't just assume that if you say the temperature increasing shows it's an exothermic reaction, they will say that you clearly understand that the opposite is true as well. So write down both of them, just to be clear that they know that you know what you're talking about. You don't want to lose a mark for something that you really do know. All right, now you need to say, how do you know which energy change is greater? Well, the one that has a larger temperature change has a larger energy change. So the larger temperature change has a larger energy change. All right, and that's the end of this question, and it's also the end of this exam. I hope you found this useful. I hope you'll do really well on your exams. If you do like this video, please press the like button. And if you haven't subscribed, we'd really appreciate it if you'd subscribe. If you have any comments you'd like to leave for us in the discussion section below, we'd really like to hear from you. And have a great day.